Oh, good evening. I was just reading this book, Einstein's Unfinished Symphony. It chronicles the conception and development of the Laser Interferometer Gravitational Wave Observatory, or LIGO for short. It's a special observatory. It was created to put one of Einstein's most extreme predictions to the test. It doesn't look for light like other observatories. No, it looks for ripples in the fabric of space-time. In addition to inventing calculus, Sir Isaac Newton was one of the first physicists to provide a detailed explanation for the phenomenon we know as gravity. And despite referring to it as an inexplicable, mysterious force, his explanation served us well for about 200 years. But in the late 19th century, the physics community started noticing holes in his theories, scenarios in which Newtonian mechanics did not suffice. It wasn't until 1915, when Einstein published his theory of relativity, that he proposed that space and time were actually the same thing. Not only that, but that they formed a fabric, if you will, that held reality as we know it together. Like any fabric, it could be bent and warped. And it went on to say that these distortions were caused by objects of large mass, and that gravity was not a force, but merely a consequence of that mass bending space-time towards it.
Hey guys, to start things off, let's check out this demo about flat spacetime. The black mesh surface you see here represents spacetime. Spacetime is essentially flat in the absence of gravitational sources. An example of a gravitational source would be a large collection of masses or a large mass like the Sun, for example. Away from any gravitational sources, spacetime can spread out and is essentially flat. We can see that demonstrated here as the billiard ball rolls across the black mesh. Without any significant curvature in the fabric, the ball is free to move along in a straight line at a fairly constant speed. This motion is consistent with Sir Isaac Newton's first law that an object in motion tends to stay in motion. And what he really meant by that was that an object will continue on its existing path at its existing speed until some external force interferes. But what Newton related to as a force, Einstein proved was something else entirely. Now in this next video, what we see is a massive object in the center of the table, and this mass has warped the shape of the fabric on which it sits. We could say that it has produced a well around it, and we can see how the sides gradually slope downward toward the ball. This is a good analogy for how mass warps space-time. We can see that as an object approaches, instead of falling along its path in a straight line like in the earlier video, it encounters the curvature produced by the ball, and that curvature manipulates the path the marble takes. The marble has fallen into this well and is stuck, riding along the edges, orbiting the ball to the center.
As other masses traveling through space come close enough to this center mass, they experience the effects of its space-time curvature. You can see they begin to circle it just as the planets in our solar system orbit the Sun. The main difference, of course, is that there is a decent amount of friction between the sheet and the marbles, which causes them to slow down and spiral inwards pretty quickly. Comparatively, the planets in our solar system experience no friction in space and actually move slowly away from the Sun. As the Sun burns its fuel, its mass and gravity decrease, a result of the curvature of space becoming more shallow around it. If you've ever sat outside at night, you've probably noticed that big yellow moon moving across our sky. But if the Earth orbits the Sun, why doesn't the Sun pull the moon away from it? Well, let's take a look. As we can see in this demonstration, the planet that the moons are orbiting produces its own curve in the space-time around it. It's just deep enough, and the moons are just close enough that they ride that smaller curve while the whole system rides along the curve from the sun. Then, as they get closer to the center, because of the friction of the sheet, we can see the moons get ripped from the planet as they fall into the gravity well formed by the sun.
Finally, let us consider a galaxy. What you might not know is that galaxies have an overall rotation to them. Now, how this came to be is what we have our very own alien specialist here for.
This, my friend, is a magnificent question, and the answer must clearly lie within the stars. But to me, this just screams extraterrestrial intervention, right? Well, let's have a look. And this time, how about we play the aliens, and this time, we introduce some chaos. Let us introduce many sets of marbles, each with a unique starting orbit direction and speed. Watch closely here, as otherwise you might miss what happens to chaos over time. You see, no matter what direction the marble moves in initially, there will always emerge order. Order in this case is the orbit of all remaining marbles in a unified direction. So, you see, from chaos became order, and that is what we see today. When we consider a system such as our early universe, where chaos was part of everyday life, well then its natural next step would be order. And that's what we see. That's what we see when we point our telescopes to the sky and we see rotations and we see orbits. That is what we see. Well, I suppose this doesn't prove the existence of extraterrestrial life.
It's false. No way. Not this time. We created it. Not this time. No, not this time. It's totally made up.
But what it does prove is that Einstein's theories that he set up so long ago actually make sense.
The space-time demo shown in this video can easily be created at home. In order to create one, you will need the following: a rubbery or stretchy fabric, like the tablecloth shown in this video, a hula hoop or other circular object with an open center. In this video, we used PVC pipes to create a circle. Binder clips, tape, or other strong methods of holding the fabric over the circular opening. Binder clips are nice because they're temporary. Finally, some spherical balls with enough weight to displace the fabric when placed on it. Once you have these materials, simply stretch the fabric across the circle and attach it to the sides of the circle using the binder clips or other materials. For the best results, the fabric should be taut and flat when nothing is placed on it. I encourage you to experiment with different types of setups like the ones shown in the video as well as others that we haven't showcased.